I did a little switcheroo on the title on you guys. Sorry, I thought I was going to be in the astrochemistry session, so I modified it a little bit to make it a little bit more relevant to that. But we just got a boatload of data from the Hubble Space Telescope on low-mass stars that host planets, and I'm going to give you a little tour of what we see in those data. OK, so first, here's how we're going to do it. I'm going to tell you about what MUSCLES is and why we undertook this survey. And then a quick little bit about spectra, and then we'll get into what I think is the most interesting, which is flares that we see in these data. And then a little brief overview of what some of the possible implications of those flares are for exoplanet atmospheres. All right, so starting with MUSCLES. All right, just like most acronyms in science and engineering, it's pretty contrived. It goes measurements of the ultraviolet spectral characteristics of low-mass exoplanetary systems. So first, let me shorten that a little bit so I can fit it on the top of a slide. And then let's unpack the two important parts of this. First of all, why the ultraviolet spectral characteristics as opposed to other parts of the electromagnetic spectrum, and then why low-mass exoplanetary systems. So I'm going to go in reverse order. Since it's near lunch, I will go ahead and give you this little introduction to spectral types of stars, even though this was briefly discussed earlier. Of course, astronomers refer or classify stars using this lettering system, which doesn't really make that much sense because it's not ordered by the alphabet, but it has historical reasons for that. And basically, these stars on the left are, as you can see, the M and K stars are cooler. They're redder, which means they're cooler. They're smaller. They're less luminous. And as you go to spectral types F, A, B, and O, they get bigger and hotter. The sun's a G star, and the low-mass stars that I'm talking about are M and K stars. And I'll probably eventually mess up and say M dwarfs, even though I don't want to do that to you guys because it makes it sound like these stars are like irregular or something, that they are not a normal size. But it just means that they haven't become giants yet. So if I say M dwarf, I mean a regular M star. All right. So the reason we care about these M stars is because basically there's a lot of them, and you all probably seen this sketch from XKCD. And all of the gray dots on this represent, statistically at least, planetary systems within 60 light years of Earth that should have stars that are smaller than the sun, essentially. And the red points are sun-like stars, and the gray points make up about 90%. So by sheer numbers alone, we should care about low-mass stars when we think about planets. OK, so now you know about the low-mass part of that title. What about the UV? Well, here is a stellar spectrum. I have modified the scale a little bit, so the black body part of this spectrum actually fits on the diagram. But we're actually not going to talk about the black body at all. Instead, we're curious about the UV because photons in the UV have about the right amount of energy to split atoms off of molecules. So, for example, you can dissociate oxygen. And we were also curious about slightly shorter wavelengths, the X-ray and extreme ultraviolet, because these have enough energy to eject an electron from an atom. And this actually plays a big role in heating the upper atmosphere of planets. So that's the ultraviolet part of this. OK. So before I go any further, let me just plug our main spectral data product real fast. We managed to we managed to write 3 very informative papers about how we reduce these data and everything that went into getting spectra that go all the way from the X-ray to the infrared. And actually, there is a ton that goes into it, so the 3 papers were necessary. And for you photochemical modelers out there or anybody else who's interested, you can find these spectra by going to that link or searching MUSCLES spectral catalog, which has the additional benefit of giving you some interesting Google image search results. OK. So now let's go on to some more results. Basically, I just have one slide of this, and then we'll get to flares. The main result is that these stars are actually all kind of similar, at least in astronomy terms, which means order of magnitude, as far as what fraction of light they emit in their photochemically active ultraviolet part of the spectrum. Same is true for the extreme UV, but they all are somewhat elevated relative to the sun. The cool thing about this is it means that once the Hubble Space Telescope dies and we can't get ultraviolet observations anymore, if you want to do photochemical modeling, you can sort of just pick a good median star in here, and you'll at least know to within an order of magnitude, you're kind of on the money. All right, so the cool thing about these observations is that we can look at them both spectrally, but also temporally. We can split them up in time. And so for this next part of the talk, I am just focusing on the UV purely. And these are the only observations for which we have several hours of data and for which we can actually spice things up in time. So when you start cutting that up in time, what you see is that, I'm going to skip this real fast, not super necessary. You see that the ultraviolet emission, which is mostly manifested in a few very narrow emission lines, it often flares to quite an extreme extent. So for example, emission from this one emission line went to 100 times its quiescent level during this flare. And we saw this on 5 out of 7 of the M stars that were in the survey. So it's common, even though these M stars are basically normal, or typical, I guess you would say. They don't stand out from stellar populations in any particular way. So flares are a big deal in these stars. They're happening frequently enough that even with 3.5 hours of observations, you can see one. So then I can look at these flares statistically, make cumulative distribution plots like this, where you have how frequently the flares occur if they have an energy less than or equal to the value on the x-axis. And this is similar to like crater counting diagrams, or I think something in biology would be like a lifetime plot. So the stars in our muscle sample fall right here. They're sort of in between the sun down here on the bottom and some stars that have been the subject of a lot of observations because they flare a lot. So we knew that they were pretty interesting. So again, flare is significant. And last night, I decided I would integrate this and see just how much energy a planet might receive from these UV flares. And the answer was a little surprising. It was enough to obliterate quite a few Earths, which, I guess NASA should have consulted me before they sent Kepler up there and wasted all that money. I could have told them that they weren't going to find anything. But I think the real problem here is that I don't know what's a good upper limit for the integration. And what I used was, what's the highest energy where you get one flare in the life of the universe? And I imagine that the real upper limit is much lower. But that's something I'm going to be exploring in the future. OK, so what do these flares mean for atmospheres? Well, here I'm just going into the literature to give you all some perspective. There was a group that published a paper in Astrobio in 2010 where they exposed an Earth atmosphere to the largest flare that's ever been observed on an M star. And if they incorporate just the UV light, they get somewhat modest depletions of ozone, factor of few for ozone, and a few orders of magnitude for, or 1 order of magnitude for water. But there's not much water up at the levels where they saw that. So here you're looking at basically amount versus altitude. But then they decided they would incorporate particles, which, as you might know for the sun, often flares are associated with ejections of particles, which do things like mess with our power grids. And when they did that, they got pretty substantial depletions of ozone. It almost goes away in the upper atmosphere. The result is a reduction of the ozone column to, I think, about 10% its original value. And so that's pretty significant. It might sound like that might be damaging for life, but 10% of ozone is still OK. And then there was this really interesting paper recently by the AbGradCon group where they suggested that if you expose the early Earth atmosphere to flares like these, then you might actually produce some biologically relevant molecules. And in fact, these are also greenhouse gases, so they could help solve the faint young sun paradox. So basically, flares are important. But there's one caveat, one important thing that this brings to mind. I hope you all can read this in the back, but a question that we need to answer is just how many particles are actually coming out of these M-dwarf flares if M-dwarf flares are so frequent and strong. And we have pretty good reason to believe that it might be different than the sun. We might not just be able to scale the sun in this case. But until we have measurements, we don't really know. And so far, we don't have any measurements. So with that, I'll leave the conclusions and take any questions.
I'm going to ask the first question this
Yeah.
time. So you said that you got a 5 out of 7 of these had these flares while you're observing it over 3.5 hours. So
Yeah.
can you back out an expected actual frequency of the flares? How often, on average, are these flaring? I mean, is it once every 3.5 hours? Is it?
Yeah, it's about, yeah, if you divide it by the 7 stars, you get about 1 every 3.5 hours. So, and these are flares that, so the one I showed you, of course I showed you the best one, and that was 100 times, an elevation of 100 times the quiescent level. But the other ones are about 10 times minimum, so they're all pretty strong in the UV.
So great talk. Are these flares that are coming out directional? And if so, what's the probability that they would actually be hitting the planet?
Yeah, this is something I haven't explored fully either. And I am sure that of course, you have to be at least on the right hemisphere of the star. The flares are so short that the star is not going to rotate into the view of the planet over the course of a flare, for at least the flares that we saw. So direction matters, and but I don't have any good answer for like how directed it should be.
Any other question? Yep.
So you said that to measure the particle flux, you can't just scale down the sun. So is there any plan to study M dwarfs in the near future to like try and back out what their particle flux is compared to like what we do with our sun, and then comparing it to other sun-like stars?
Yeah, the most intriguing plan that I've heard is I know, and hopefully I won't murder this because I don't know much about this particular type of observing, but I know there's a group that is attempting to get radio observations where you could see emission from the particles as they spiral out on the magnetic field lines from the star. And that would be an awesome, basically direct measurement of the particle fluxes. So that's what I'm waiting for personally.
Any other questions? All right, thanks, Parke, again.